Hello everyone, my name is Ju-Young Kim. I'm the CEO of HyperAccel. So at HyperAccel, we are innovating AI processing by building a specialized chip for LLM inference. We have our own processor technology called LPU, and we also have a core networking technology for multi-chip scalability. And we are focusing on practical solutions by targeting the first and the best LLM chip without HBM. So we founded our company in January 2023. We are only 1.5-year-old company, and we are now 30 employees. So far, we've raised $4.6 million as seed money, but we already launched our first server product called Orion based on FPGA accelerators. And we are making 4nm ASIC right now. For my background, I got my PhD in chip design, and I joined Microsoft to develop a hardware accelerator for data centers. And I came back to South Korea as a professor, and we've done R&D and system prototyping for 2 years before we found the company. So here's what we do now. So this is a demo video of our Orion server running the latest Llama 3. So the left side is the Orion server, and the right side is the Meta AI service. And as you see here, our server gives us the quicker response than the Meta AI server. And when we ask about the unit code generation, you can see that it can generate the code very well. And we also asked to write some algorithm code in Python. And as you see here, it can generate very well. So like you see here, what we are trying to do is to accelerate LLM inference with our own hardware accelerator, making faster and more sustainable, meaning less cost and less power. So as you all know, the chip market is growing very fast. And among the sectors, LLM inference that we are targeting grows fastest. It will become a $128 billion market by 2032. Then why do we need a specialized chip for LLM inference? The reason is that its base model called transformer has very large model, and you need to read the model again and again sequentially to produce the output tokens. This actually makes it super memory intensive, and if you run this with GPU, most of the processing cores will be idle, doing nothing. So if you think about the cost and the power of GPU, this is very inefficient. So we actually need a kind of bespoke chip for LLM inference, and we call this LLM processing unit, or LPU. So now, let me tell you why HyperAccel's LPU can be the best processor for LLM inference. So as I briefly mentioned, the transformer model reads the big model again and again to produce the output tokens. So the most important hardware metric here is the memory bandwidth. How you effectively use it actually determines the overall system performance. So our LPU has streamlined memory access technology, which can utilize the memory bandwidth up to 90% for a given bandwidth, while the GPU can only achieve 50 to 60%. Along with that, our streamlined data flow architecture, which is our core technology, maximizes both internal bandwidth and the logic utilization. So here we show you the conventional NPU GPU architecture, and you actually cannot see the characters there, but the model parameters stored on the off-chip memory will be fetched into the on-chip buffer. And if you look at the right side, there is a compute unit, and this compute unit has lots of small processing elements in which each has 1 to 4 multipliers. And when they run LLM inference, they have to move the data back and forth between the on-chip buffer and the compute unit for many times. This actually causes the whole data flow stalling in the middle, and this is why it cannot utilize the given bandwidth, and it only uses by half. On the other hand, again, the characters are broken here, but the parameters are stored in a formatted way, so it can actually directly fed into our LPU core. And this LPU core is a quite big core that can cover all the operations required in LLM inference, including attention, normalization, feed-forward network, nonlinear functions, and the top K, top E, all the different algorithms. So by having only necessary part on its L1 cache, since it can cover all the operations, it doesn't have to move the data back and forth between the memory and the compute unit. Moreover, it can send the model data to the next LPU core so that it can reuse it. So in overall, the data flow is really streamlined, and the data are reused over multiple cores, and it can generate the output token seamlessly without any stalling in the middle. So as a result of this, even with less number of processing cores, LPU can achieve high tokens per second performance, which is most important in LLM inference. And our LPU processor is really designed modular and flexible, so it can actually adapt the changes in the hardware specification. So if you need more memory channels with HBM, we can adapt it, we can expand the memory channels. And if you need more batching on the output side or input side, we can adapt it with the parameters. So it is really ready for silicon IP so that we can design high performance server chip or low power on-device AI chip. So far I've talked about the core technologies inside of the chip, but of course multi-chip scalability really matters here because you cannot run it on a single chip because the LLM size becomes larger and larger. So for multi-chip scalability, we develop expandable synchronization link or ESL technology, which is more advanced from the NVIDIA's NVLink technology. We also provide the peer-to-peer networking using Ethernet, like NVIDIA's NVLink. But on top of that, our LPU can handle network instruction as well, so we don't need any assistance from CPU like the NVIDIA case. It can actually handle everything without any assistance from the CPU. So with that in mind, if you look at this timing diagram, what the conventional processing does is that you need to compute finish the computation part and do data communication for synchronization. But these two happens in sequence. But with the NVLink technology, you can actually shorten the communication time so that making it faster, but you cannot remove it from the system level. So if you actually scale out with the multiple GPUs, this communication overhead will actually lag the entire performance down. But with our LPU's ESL technology, we can overlap the computation and the communication part. To be more specific, we go with the first tensor computation and then do the data communication. But at the second time, computation can go to the second tensor computation. So we overlap the computation and communication in parallel. And by doing this, we can effectively eliminate whole data overhead of the data communication. So when we increase the number of chips from 1, 2, 3, 4, and 8 and beyond, we don't have any overhead of communication, and we can get actually very good performance scalability. So here is our product roadmap. We launched our Orient server last October, and we've gone through all the rigorous system level verification and performance POC. Then now we are making 4nm chip with the same design. So we've already done MPW tape out in May last month, and we're gonna finish our product chip design until the end of this year. And we're gonna fab that in early next year so that we can get the chip product. So we're gonna use 4nm Samsung process, but at the same time, as I mentioned before, our LPU is also ready for IP so that we can license this to SoC builders like Intel and Qualcomm so that they can build their own on-device edge chip. So if we succeed in production chip, we expect a lot of boost in the performance, throughput performance. Currently, we got 175 tokens per second with our FPGA-based server, and we expect more than 1,600 tokens per second with our ASIC chip. That will be about twice more throughput than the latest H100 GPU. And as I mentioned, with the networking technology, we can actually get better performance scalability when we increase the number of chips 1, 2, 4, 8 and beyond. And if we set our chip price a little bit less than $4,000, we can get 19 times of cost efficiency and 12 times of power efficiency than the GPU platform. This is possible because we designed our processor really specialized for the LLM, and we measure this for the LLM workloads. But you know, the LLM workloads becomes more significant, and this strategy is really valid. And the Grok solution is really well known here in the United States, so we compare our Orient server performance against the Grok solution. So in our Orient server, we only use 8 FPGA accelerators, and we got 24 tokens per second throughput for 70 billion model. On the other hand, Grok got 284 tokens per second performance, but behind that, they used more than 500 chips for that. And each chip costs about $20,000. So if you compare the cost of it, we only use like 19 times less cost than the Grok solution. And if we actually build an ASIC from this, you can actually see that the benefit will go far beyond it. So we have 3 product lines. We already have Orient server, which is specialized for low latency processing. We are building ASIC chip for data center application, but we do have IP as well. So we have some inbound calls from the edge SoC company who want to use our LLM IP for their SoC. So, you know, we're still at early stage. And we are open for Series A funding right now. We are seeking $40 million for 4nm chip production. And if you're interested in, just let me know, Kim@hyperaccel.ai. And we also have a demo booth over there. You can try our Llama 3 lively running on our server. Thank you for listening.